The goal of this video will be to ultimately define what limits and colimits are in category theory. And in order to do that, we'll need to build up a few definitions first. So the concept of a limit relies on the concept of a cone, and so we'll need to define what a cone is. And the dual concept to the limit, the colimit, will rely on the concept of a cocone. So we'll need to define cones and cocones first. And in order to do that, we need to define more rigorously what a diagram is. So we have seen diagrams in the past, but we haven't really talked about them too rigorously. So we'll define what a diagram is first, and then use that to define cones and cocones over diagrams. And that will allow us to define limits and colimits in the end. So that will be the ultimate goal of this video, but we'll start with what a diagram is specifically. So suppose I have some category C here with morphisms A, B, C, and E, where A goes from A to B, B goes from B to D, C goes from C to D, and E goes from D to E, and have this sort of pattern. And maybe there's more going on in the category. Obviously, there will have to be more going on in the category because we would also need identity morphisms on all of these, and we would need morphisms that correspond to compositions. But we've drawn a certain number of morphisms in this category C. And we want to isolate, for some reason or another, we're interested in a specific pattern that we want to isolate. So say, for some reason, I'm particularly interested within the category C in this pattern right here, where we have A going into B and B going into D, and then we also have another morphism C going here from C to D. So I'm interested in that specific pattern for some reason, but I want to be able to isolate that specific pattern or collection of morphisms and objects that I'm interested in so that I can talk about it and only it within this larger category. And so what we can actually do in order to do that is let's just construct alongside here a toy category that only has the morphisms of interest. So I have an object here, maybe object number 1, and it maps into object number 2 here by some morphism alpha, and then 2 maps into 3 here like this, right? This one, maybe we call this beta, and then C, which in this case would be object 4, I guess, gets mapped into 3 by some morphism, maybe call it theta. So what we do is we just construct only the pattern that we're interested in this category, and we map it via functor into this category, so that now maybe we have some D, the functor that maps our category here, which usually is referred to as the index category. Could maybe call it J. So it's an index category because it's simply just indexes, right? 1, 2, 3, 4. Obviously, it doesn't have to be restricted to natural numbers. There could be an uncountable number of objects in here. So there's no restriction that it needs to be natural numbers that index it, but there's some index category that maps onto our category of interest, so that now when I talk about the image of the functor D, the only objects that I talk about and the only morphisms that I talk about are the ones contained in this portion, the portion that I'm interested in specifically. So what is a diagram then? Well, it's just a functor. In this case, we called it D, going from our index category J into our category of interest C. That just creates a toy example, basically, of the pattern that we're interested in, and then maps it onto the category that we're interested in. As I mentioned, though, there's actually no restrictions on what this index category looks like. And what that means is that actually any functor whatsoever can be thought of as a diagram, and any diagram can be thought of as just a functor. So although really usually what we call the diagram is this portion here, what we're actually talking about when we talk about a diagram is always a mapping from an index category into the category of interest. And so the diagram here that we usually refer to is actually the image of this functor. But the only restriction, obviously, is that this needs to be a well-defined functor, and therefore J needs to be a well-defined category. And something that you'll notice here is that this is not a well-defined category, right? Why is it not a well-defined category? Well, because we need to have identity morphisms on every object, which are not drawn here, and we need to have composition, for example, of these two morphisms here, which needs to exist in this category as well. But the way we think about it is we just say that we can always implicitly refer to any identities or any compositions. So that basically guarantees that our index category will always satisfy the definition of a category, because we're basically forcing it to. We're saying, yeah, whatever I draw here, it doesn't matter. You can always add identity morphisms and talk about them, or you can always talk about the composition, so that these categories can be well defined and this functor can be well defined. And obviously that will be true on this side as well. We will always have, even if they're not drawn, we will always have identities and compositions defined in these categories to make this functor well defined. So that's the definition of a diagram. It's actually not really anything new. It's literally just any functor. But usually, as mentioned, it's a functor which allows us to map some specific pattern onto a category that we're interested in. So just remember that a diagram is just a functor, and it could be any functor. There's no restriction, but usually it's used to isolate a specific pattern, that is, a specific collection of objects and morphisms between them in a category that we're interested in. So that's the definition of a diagram. So how does the diagram allow us to define a cone? Well, a cone consists of some object V here, and V is actually in the category C, so we can kind of think of V in this category here, C. Maybe remove this to show that it's all part of the same category. And what V does is it has one morphism for every object in our diagram, mapping from V into that object. So we have, in this case, V1 going from V to the image of the object with index 1, so I'll call this V1, V2, and the third object is D here, so this would be V3, and 2C would be V4. Now the cone consists of the vertex V and all of the legs VI, where each VI goes from V into the object under D of the object of index I. And not only that, but all of these triangles created by these morphisms and the morphisms in the diagram need to commute. So for example, it must be the case that V4 followed by C here has to be equal to V3. Right? And same for any of the triangles created by these morphisms raining down and the morphisms that exist in this diagram. And if that's the case, then this pair V and the set of VIs is called a cone over the diagram D, the diagram functor D. So this is a cone over the diagram D. But an important thing to note here is that there's no reason we couldn't have another cone over D Maybe this time with a vertex W and legs WI, where each one of those is the same, going from the vertex W into all of the images of all of the index objects. So here's some other object, W, in the category C, which is another vertex, which has a morphism going into each one of these objects in the diagram. And have the same index. So this is W1, this is W2, this is W3 over here, and W4. And obviously, same property has to exist here, which is that any of these triangles created need to commute. So in this case, we have A going from A to B, and we have W1 going from W into A. So it must be the case that A after W1 has to be equal to W2. And same for all of the triangles created between any of these W morphisms and any of the morphisms in our diagram. So if that's the case, then WWI, the set of WIs, would be another cone over the same diagram D with a different vertex, but there's no reason that we couldn't have another cone with the same vertex V or the same vertex W, either way, and some other set of legs like V prime I, right? And it would be different morphisms here, but they would all need to commute just like the regular ones. And if that's the case, then we could have multiple cones over the same diagram and even multiple cones with the same vertex over the same diagram. And what happens is, if we collect all of the cones over a specific diagram, we can create a cone category. And what is the cone category? Well, it has objects, which are all of the cones over our diagram D, and morphisms are just regular morphisms going from vertex to vertex, so in this case from W to V, with the property that, so say we have some L going from W to V here, which maybe I'll draw in red. So this L can be considered a morphism of the cone category if we can say that all of these triangles commute between the legs of the diagram. So that is, for example, in this case, W1 would have to be equal to V1 after L. Right? Going this way would need to be the same as going this way. And if any of these triangles commute, then that can be considered a morphism in this cone category. So in the cone category, the legs of the respective diagrams need to commute with this morphism between cones. And then within the cone, the legs need to commute with the morphisms in the diagram. So as we're used to in category theory, it all comes back to commutativity properties, but we can now see that we've defined a diagram, which is just any functor. We've defined a cone over that diagram, and we've now defined a cone category, which consists of the cones over a diagram and morphisms between them, which means morphisms between the vertices where all of the triangles created by the legs and that morphism commute. One good exercise to try at this point would be to prove that the cone category satisfies the definition of a category. So we defined the cone category, but we didn't actually show that it was well defined. So if you want, pause the video here and prove that the cone category is actually well defined. Otherwise, we're going to continue on to prove that actually any category can be thought of as a cone category in a sense, or any category can be associated with a cone category that we construct. So if we have some category D here, and we'll just add a couple random morphisms in here to this category, maybe A, B, and C, and morphisms A and C, something like that. Well, what we can do is we can create a new object, X, that's not in D, and we can create one morphism going from each object in the category to our new object, X, and we can define it such that these morphisms in the category will always commute with these morphisms coming out of the objects. So maybe call this XA, XB, and XC. Then if we add an identity morphism on X, 1X, and take this category here, maybe call this one D prime, which is just D with our new object and all of the morphisms created for that object just sort of stapled onto that category. This will be a well-defined category, and again, that could be a quick exercise. It's not hard to prove. Why is this a well-defined category as well? And if that's the case, then notice that, for example, the pair AXA can be thought of as a one-legged cone in this category, D prime. It's a cone over the diagram, which consists of just X, right? If you think of this object by itself as a diagram, then maybe call this diagram curly X or something like that. If you think of this as a diagram, which means a functor going from a category that just has a single object in it mapping into here, right? This diagram is just a single object. So it consists of a functor, curly X, going from a singleton category into this category, D prime. And it's a cone because there's no commutativity property that it has to satisfy. There's no morphisms in this diagram here, so it trivially satisfies the commutativity property. And there's one for each because there's only one. So as long as we have one from each object, then each cone over each, or for each object as a vertex will be well defined. So basically, we can associate any object A with the one-legged cone AXA, and any morphism in the category, the original category D here, for example, A, will actually be able to be mapped to itself as a cone morphism, because in order for it to be a cone morphism, all of these triangles here have to commute, but they do. That's how we defined them. So since we defined them to satisfy that property, this means that A or C as itself in the cone category will represent a cone morphism. So we can see that by this association, for any category D, or for any diagram D for that matter, we can create a cone category out of that category, and that's over a singleton diagram X in this category D prime that we've constructed. So that was just an aside to show that any category can in some sense be viewed as a cone category, or more exactly, any category can be associated with a cone category that behaves in exactly the same way. Now the dual concept of a cone, the cocone, is where we, as usual, flip all of the morphisms in the pattern that we're looking at. So in this case, all of the VI's would have to go in the other direction from our diagram down into our vertex. So it's still called a vertex of the cocone, but in this case, suppose we had our same diagram D, which consists of A, B, C, and D, with morphisms A, B, and C. Well then, a cocone would just be some vertex V, once again, where in this case the morphisms are now going into our vertex instead of coming out of our vertex. So, but in the same way, we have one for each object in our diagram, and in the same way, all of these triangles commute. So if these are V1, V2, V4, and V3, then we must have that all of these triangles created by these morphisms and the diagram morphisms must all commute. And in that case, the pair V and all the VI's will be a cocone over this diagram D, the same diagram that we had a cone for over here. And in just the same way that we constructed the cone category, we can also construct the cocone category over a diagram. So that's another exercise you can try, is what does it look like to construct the cocone category and make sure that it's a well-defined category as well. But now that we have the definition of a cone and a cocone in mind, we can now finally arrive at the definition of a limit and a colimit. So a limit is a terminal object in the cone category over D. So what does that look like? So maybe pause the video here and try to write out this definition a little bit more. What does it mean for something to be a terminal object in the cone category? Well, if it's a terminal object in the cone category, then it has to be an object in the cone category. So let's take, for example, this cone, V, and the set of VI's. This is an object in the cone category over D, as we've seen. And what would it mean for this cone to be terminal? Well, it would mean that for any other cone, for example, this WI cone, we must have a morphism going from W into V. So if that's the case, then we have a terminal cone. For any cone in the cone category, there needs to be a morphism going from that cone into our cone of interest, V here. And in this case, we do have one, which we said was L. But if we had some other new cone in the category, for example, say some cone XI, drawn the same way as we're used to. We have our vertex X here, and we have one morphism, starting to get a bit messy, going into each object in our diagram. This. And if that's the case, where this is X1, this one is X2, and this one is X4, and this one is, oh, actually, no, I drew this. This should be X3, and this should be x4. If that's the case, and again, as we know, all of the diagram morphisms commute with all of these triangles with these legs, xi, then we have to have some morphism going from x into v, which is a cone morphism, a morphism in the cone category, I should say, and maybe that one's called m. So we would need to have some sort of morphism m going from x into v. And remember, for it to be a cone morphism, it needs to commute with the legs of the respective diagrams. So we would need to have x1 was equal to v1 after m, right? This triangle here would need to commute. Obviously, it's hard to see the triangles now, but so that would define a terminal cone in the cone category, and that would define a limit over our diagram D. So just to show how much we've built up in terms of definitions, let's fully unwrap the definition of a limit. And so what we see is that a pair VI in the category C is called a limit over a diagram D, and written limit D with the arrow like that, if all of the legs VI commute with all of the morphisms in D. So that was what we saw. We need to have that everything inside the cone commutes. And for any pair WWI, which is also a cone, that is where all the legs WI commute with all of the morphisms in D, then there needs to be a unique morphism L going from V to W, from the vertex to the vertex, such that L commutes with all of the respective legs. So that was where we were saying these triangles need to commute. That is, VI after L has to be equal to WI for all of the I. It's important to note that there needs to be a unique morphism L from the vertex to the vertex, and that's in order to satisfy the definition of a terminal object. So a terminal object in a category has exactly one morphism going from every object into that object in the category. So in this case, our terminal cone needs to have exactly one cone morphism going into it from any other cone in the cone category. So as you can see, we've managed to pack quite a sophisticated concept into this definition of a limit, and it's quite difficult to remember it this way, but if you remember it as just a terminal object in the cone category over a certain diagram D, then that makes it a lot easier to understand. So next, let's look at the definition of a colimit. So to get the definition of a colimit, we need to take the dual of a limit, and that is we basically take the dual of every concept in our definition. So in this case, it's a terminal object. So for a colimit, it needs to be an initial object. And in this case, it's in the cone category. So for a colimit, it needs to be in the cocone category. So what that gives us is that a colimit is an initial object in the cocone category over D. And so in a very similar way, you can unwrap the full definition of that, and that would be a good exercise. Try to write out the full definition the way we did for a limit for a colimit, and note that the notation for a limit is limit over D with the arrow pointed backwards, and the notation for a colimit is the limit over D with the arrow pointing forwards. Thanks to presenting the definitions in this way, we basically get a theorem for free, which is that limits and colimits are determined up to isomorphism. That is, if any two objects are isomorphic and one of them is a limit, then the other one is a limit, and if any two objects are limits, then they are also isomorphic. And the reason we have that is because any two terminal objects in a category are isomorphic, and any two initial objects in a category are isomorphic. So because terminal objects and initial objects are determined up to isomorphism, it follows that limits and colimits are also determined up to isomorphism. So we can sum up what we've defined pretty succinctly here in a result that we got for free at the end. And to conclude, I'll just mention that limits are a generalized definition, so it's a terminal cone over any diagram. But if you talk about different types of limits, usually you're talking about a limit over a specific type of diagram. So what I mean is, for example, if I have a diagram in a category and there's no morphisms other than identity, which are always defined, if I just have three discrete objects like this in my category, and I have a limit over this type of diagram, D, then it's actually called a product. So if I can find a terminal cone V and VI's over this diagram, then this cone is actually called a product and coincides obviously with the definition of a categorical product. So we'll see that in future videos, and we'll also see other different types of limits, which means limits over different types of diagrams, different patterns in this diagram.